Good morning, students. Hope this video finds you well. In this video, we will study about Kruskal's algorithm. Kruskal's algorithm is an algorithm from graph theory. The prerequisite for this video or learning Kruskal's algorithm is graph theory, what is a graph, and some terminologies of graph. For a quick revision, a graph is a set of vertices and edges. These vertices or nodes hold information, and the edges gives us the relationship between the nodes. So let us begin with Kruskal's algorithm. Okay, so Kruskal's algorithm is to find minimum spanning tree of a given graph. So let us first understand what is a spanning tree. If you're given a graph G, then a spanning tree is a subset of the graph G such that it has all the vertices in G, but it has the minimum possible edges. Okay, so we will not take all the edges in the graph. We will take all the vertices, but minimum possible edges. Also, the spanning tree does not have any cycle, and at the same time, it cannot be disconnected. Thus, the name tree, because a tree is a graph which does not have any cycles, but it cannot be disconnected. So let us look at this example. We have a complete graph here, and from this graph, we can make three different spanning trees. So from this example, it is clear that a given graph can have more than one spanning trees. And a formula is given here. If the number of nodes in a given graph, number of vertices in a graph is n, then n raised to the power n minus 2 will be the maximum number of spanning tree that the complete undirected graph can have. So in the above example, as we have three vertices, so 3 raised to the power 3 minus 2 equals to 3. So there are three possible spanning trees of this graph. Let us also look at some of the general properties of a spanning tree. A connected graph G can have more than one spanning tree. If we have a connected graph, then we will have more than one spanning tree. All spanning trees of the graph will have same number of edges and vertices. As we have seen in the previous example, they will have all same number of vertices because it is compulsory for us to include all the vertices. So number of vertices will remain n only, but the number of edges will also remain same in all the spanning trees of a given connected graph G. Then, most importantly, a spanning tree does not have any cycles or loops, which is essential because that is why we are calling it a tree. We know by the definition of tree that a tree cannot have any cycles or loops. So the spanning tree will not have any cycles or it will not have any loops. Removing one edge from the spanning tree will make it disconnected. So as we already said that a spanning tree is connected. So even if we remove one single edge from the spanning tree, then it will become disconnected because one of the vertices will become isolated from the rest of the tree. So this will be called minimally connected. Similarly, if we add one edge to the spanning tree, it will create a circuit or a loop, and then it will become maximally acyclic. So these were some of the general properties of a spanning tree. Spanning means पहुंचना, reach होना सब तक, सारे nodes तक. That is why the word spanning tree. Okay, so if we have a weighted graph, for just a quick recap, a weighted graph is a graph in which each edge is assigned a weight. Let us see a quick example like this. Each of the edge in the graph will have some weight. So if in a weighted graph, as we know that a graph can have more than one spanning trees. So the one tree which has the minimum weight, how will we find out the weight of the spanning tree? We will simply add the weight of all the edges in that spanning tree. So the spanning tree which has the minimum weight will be called the minimum spanning tree. So there are two important algorithms for finding out a spanning tree from a given connected graph G, namely Kruskal's algorithm and Prim's algorithm. And in this lecture, we will be studying about the Kruskal's algorithm to find the minimum spanning tree, also sometimes called MST of the connected graph G. So the Kruskal's algorithm uses greedy approach for finding the minimum spanning tree. By greedy approach, we mean to say that at every step, we will find out the local minima, and we will assume that in this way, finding local minima at each step, finally, we will be able to reach the global minima or global maxima if we are finding maximum of something. As in this particular algorithm, we are trying to find the minimum cost. That's why we will find the minima, global minima, by finding the local minima at each stage. This approach will become more clear when we will look at the example of Kruskal's algorithm. The Kruskal's algorithm treats the graph as a forest. A forest is nothing but a collection of trees. As in a general sense, we say when there are n number of trees, a collection of trees, then we call it forest. Similarly, in graph theory, when there are n number of trees, then we call it a forest. So the Kruskal's algorithm treats the graph as a forest. Initially, every node in itself is a tree, and it's simply a collection of trees, and thus the name forest. We will form a tree out of it by adding edges to it. So initially in Kruskal's algorithm, we do not have any edge. We simply have all the vertices, and then we will be adding edges to it. A tree connects to another if and only if it has the least cost. Okay, so the edge we will be adding to the this tree for formation of this tree will be the one which has the least cost, and at the same time it should not violate the MST properties. And here by MST properties, we most importantly mean that it should not form a loop or a circuit. Okay, so let us go through these steps. First step is remove all the loops and parallel edges. As soon as you have your graph in front of you, first thing you will do is you will remove all the loops and you will remove all the parallel edges. Then arrange the edges in increasing order of their weight. We are required to add the edge with the smallest weight every time. So it is better that we will get them sorted in increasing order of their weight. At the edge which has the least weightage. Okay, once we have arranged the edges in ascending order, each time we will take a edge which has the least weight, lowest weight, and conclude the process when all the nodes are included. Once we have a connected graph, then we will conclude the process. Even if some edges are remaining, we will just leave them be because we have already got our tree. Okay, so let us understand whatever we have learned about the Kruskal's algorithm from this example. This is the graph which we have in front of us. The first step that we have seen was to remove all the parallel edges and loops. So as is evident from this graph, it has one loop. What is a loop? When an edge connects to itself. When an edge connects to itself, then it is called a loop. As here, we can see that C is connected to itself by this edge. So we will remove this loop. Again, between vertices A and B, we have two edges, two parallel edges. One edge is AB, which is having the weight 9. Another edge is again AB, which is having the weight 6. So what we will do, we will remove the loop. Also, we will remove one of the parallel edges. Now, again, which edge should be removed? And I think the answer is obvious. The edge which has lesser weight will be kept. So we had two edges AB, one having the weight 8 and another having the weight 6. So we removed the edge with the weight 9. So and we kept the edge with the weight 6 like this. Also, the loop has been removed. So the first step which says that remove all the loops and all the parallel edges has been achieved. Now, let us move to the next step. And what was the next step? To arrange all the ages in ascending order of their weight. Here we can use the priority queue data structure, and in this way we can arrange all the ages that we have. Okay. So here we are getting the least cost as 2 and the highest is 8. Now we will start adding edges to the graph, to the tree, sorry. So when we look at our collection of ages or our priority queue data structure, the ages with minimum weight are BD and DT having the weight 2. So we first of all add these two to our minimum spanning tree. By adding BD and DT, we can see that no properties of the minimum spanning tree are being violated. They are not forming any loop. So we add both of these edges to the spanning tree and move on to the next edge selection. For the next edge selection, as is evident from the graph, we have AC and CD. Both of them have the weight 3, which is the next least weight. And as is evident, by adding AC and CD, no loop is being formed. So we can add these two to the graph like this. So by now we have added 4 edges and we have added 5 vertices. Now we can see that only one vertex is remaining, which is still disconnected. And what we will do is we will add the edge with the least weight. We have added the edges with 8, 2 and 3. So the next obvious choice is the edge with the weight 4. But we can see that if we add the edge with the weight 4, which is namely CB, by adding CB, we will form a circuit between the nodes C, B, and D. So we cannot add this edge. We move on to the next stage, which will be with weight 5. But when we add this edge BT with weight 5, we see that again it is forming a circuit BDT. So again, we will have to discard 5. We cannot add it to the spanning tree. We move on to the next weight, which is 6. And if we add 6 to our minimum spanning tree, again, we can see that it will form a loop. It will form a circuit A, B, D, C. So again, we discard 6. So we have added 4 edges with weights 2 and 3 by now, but we cannot add the edges with weights 4, 5, 6, CB, DT, and AB. Why? Because by adding them, it will result in a circuit, and we cannot have a circuit in a minimum spanning tree. So we have discarded all 3 edges. We move on to the next remaining 2 edges, SA and SC. Both of them can be added because they are not forming any circuit. But as is our rule, we add the edge with the least cost. So we will add SA with the weight 7. So we have added SA with weight 7, and this is our minimum spanning tree with 5 edges and all the vertices. And this is how we can calculate the total weight of the minimum cost spanning tree, or the minimum weight of the spanning tree, by adding the weights of all the edges. And here we are getting it to be 17 units. The time complexity for Kruskal's algorithm entirely depends upon the number of edges or number of vertices in the graph. So it is either order of E log V or order of E log V. So thank you so much. This was all about Kruskal's algorithm in today's lecture.